example number 5.14. There are three parts in this example: part A, part B and part C. In this example, there is an alternator with synchronous reactance 0.8 per unit. This alternator is connected to an infinite bus at a rated voltage. Therefore, the terminal voltage of the alternator will be 1 per unit. The rated voltage equals to 1 per unit voltage. Because the alternator is connected to the infinite bus, therefore we can say that the terminal voltage of the alternator is 1 per unit. It is also given that the excitation EMF of the alternator is 1.3 per unit and the alternator delivers output of 0.5 per unit. We have to neglect all the losses. In part A, we have to calculate the load angle, armature current and the power factor of the alternator. Let me discuss this part A. This is the synchronous generator with the reactance equals to 0.8. This alternator is connected to the infinite bus at the rated voltage. Therefore, the terminal voltage is 1 per unit. Always remember that the terminal voltage is taken at reference. The terminal voltage is always taken as a reference voltage. Therefore, make it 0. So it will be 1 angle 0. The EMF, internal EMF or excitation EMF is 1.3. Always remember that the excitation EMF leads with the terminal voltage by an angle delta. In the case of alternator, the excitation EMF leads because of the leading nature. I have written plus delta. The alternator is delivering current IA1 and we have to calculate, also it is written in this question that the power delivery or the power output is 0.5 per unit. We have to calculate the load angle, the armature current and also we have to calculate the power factor cos phi 1. You can write delta 1, IA1 and cos phi 1. These three things we have to calculate. In the part B, it is given that the excitation EMF is changed, which results in the same power output and the same armature current. Same armature current means the magnitude of the armature current for the part B problem will be same as the magnitude of the armature current calculated in part A. Under these conditions, again we have to find out the excitation voltage, EF2, load angle delta 2 and the power factor. These three things we have to calculate. In part C, we have to conclude the result. In part C it is written that of the excitations in part A and that obtained in part B, which is more likely to be used in practical situations. In the case of practical situations, which excitation should be used? Part A excitation, the excitation which is used in part A should be used in practical situations, or the excitation calculated in part B should be practically used, and why? We have to give the answer. So let us start with part A. The power output of the alternator is given in this way: EF V upon XS sine delta. The value of the power output is 0.5. The value of excitation EMF is 1.3. The terminal voltage is 1. The value of the synchronous reactance is 0.8. And we have to calculate the value of delta. From here we can calculate it. 17.92 degree is the load angle, delta 1. Now we have to calculate the current. If you apply KVL, you will get this equation: EF equals to V plus J IA XS. EF is given as 1.3, angle delta is 17.92. The terminal voltage is 1 angle 0 plus J IA XS is 0.8. From this equation we can calculate the value of current. It will be 0.5811 angle minus 30.64 degree. So we have calculated the current IA1. This is IA1. The power factor can be written in this way: cos phi 1 equals to cos 30.64, and it will be 0.86 lagging. Why the power factor is lagging? You can make the phasor diagram to understand it. This is the terminal voltage, and the internal EMF, or you can say excitation EMF, is 1.3 angle 17.92. So it will be above the terminal voltage. This is delta and this is EF1. Here you can write EF1. EF1 equals to 1.3 angle 17.92 degree. This terminal voltage is 1 angle 0, and the current which we have got here is IA1 equals to 0.5811 angle 30.64. Write it minus 30.64, and this is the angle phi equals to 30.64. Because this armature current is lagging with respect to terminal voltage, therefore we can say that the power factor at which this alternator is operating is lagging in nature. In this way we have calculated the load angle, the armature current, and the power factor. You can easily understand it, no problem. In part B, it is written that the power output remains same and the armature current IA2 equals to IA1. The excitation EMF is changed. We have to find out the excitation EMF, the load angle, and the power factor. The power output remains same. The power output can be written as the terminal voltage into armature current into power factor. It is constant. The terminal voltage, because the alternator is connected to the infinite bus, therefore we can say that the terminal voltage will remain constant. Whether you change the excitation, when you will change the excitation, there will be no effect on the terminal voltage. It will be constant because the alternator is connected to the infinite bus, and it is the responsibility of the infinite bus to maintain the constant voltage. Therefore, we can write Ia cos phi equals to constant. In part A, the armature current is Ia1, the power factor is cos phi 1. In part B, the armature current is Ia2 and the power factor, let us say, is cos phi 2. They will be constant. They will be same. Ia1 cos phi 1 and Ia2 cos phi 2 will be same. It is given in part B that Ia2 magnitude and Ia1 magnitude is constant. The Ia2 magnitude and Ia1 magnitude is same. It is given in part B. The magnitude of the armature current in part B and the magnitude of armature current in part A is same. Therefore, we can say cos phi 1 equals to cos phi 2 and phi 2 equals to phi 1. So, phi 2 will be equal to phi 1. What is the meaning of Ia cos phi constant? What does it mean? Let us understand by the Phasor diagram. This is terminal voltage and this is the armature current calculated in part A. This is phi 1. Ia cos phi means the projection of Ia1 on x-axis. Let us say this is x-axis, or on the terminal voltage axis. The projection of Ia1 will be this. This is the projection of Ia1 on x-axis. In part B, the excitation is changed, but the power remains same. When the power remains same, the projection of the armature current, the projection of the armature current will be same. It will be constant. Therefore, we can conclude that we have to make the armature current in such a way that the projection of that armature current is same as the projection of Ia1. Therefore, we can make the position of Ia2 in this way. And we have concluded that phi 2 equals to phi 1. This is phi 2. We can see clearly that in part B, the value of Ia2 will be equal to, the magnitude of Ia2 is same as Ia1, that is 0.5811. Angle, the Ia2 will be leading with respect to the terminal voltage, and phi 2 equals to phi 1. The value of phi 2 will be equals to phi 1, and phi 1 equals to 30.64. I have taken positive sign because Ia2 is leading with respect to the terminal voltage. The second position of the armature current is above the x-axis. It means that if the armature current is leading with the same angle as the current Ia1 is lagging, the alternator will be able to deliver the same power output. That's why I have concluded that Ia2 must be leading with the same angle with that Ia1 is lagging. Again, you can apply KVL in this loop you can apply KVL and you will get this equation EF equals to V plus J IA XS. Because we are talking corresponding to the part B of the question, that's why I should write EF2 and this is IA2. EF2 value is value we have to calculate. The value of the terminal voltage is 1 angle 0 plus J. The value of IA2 is 0.5811 angle 30.64. The value of XS is 0.8. If you calculate the whole right hand side, you will get 0.8615 angle 27.663 degree. The first question was we have to tell the magnitude of the excitation EMF. The magnitude of the excitation EMF will be 0.8615. The power angle is delta 2 equals to 27.663 degree, and the power factor cos phi 2 equals to cos phi 1. Cos, the value of phi 1 is 30.64. It will be 0.86, and this should be leading in nature because IA2 is leading with respect to the terminal voltage. The terminal voltage is 1 angle 0 and IA2 is this. IA2 is leading with respect to the terminal voltage. That's why the power factor is leading. In part C, we have to conclude, or we have to state which excitation should be used. The excitation which is used in part A should be used, or the excitation which we have calculated in part B should be taken into account, which is more likely to be used in practical situation. So we can see here in part A, the alternator was operating on a lagging power factor. In part B, we have seen that alternator was operating on a leading power factor. The value of EF1 was 1.3 and the value of EF2 was 0.8615. So in this question we have to say that which is more likely to be used. So your answer should be that the excitation of part A should be used. It is more likely to be used in the practical situation because the alternator is lagging in nature. The alternator is delivering power on a lagging power factor. When the alternator is delivering power on a lagging power factor, it will deliver real power plus it will deliver lagging reactive power. In the power system network, the power system needs lagging reactive power, and this alternator, which is working on a lagging power factor, it delivers lagging reactive power. That's why the EMF calculated in part A, or the EMF given, that's why the excitation EMF of part A should be used in practical situations. The EMF which we have calculated in part B should not be used in practical situations because the alternator in part B situation is delivering real power plus leading reactive power. It is delivering leading reactive power. The power system equipments, the power system components do not need leading reactive power. The power system components need lagging reactive power, and the alternator in part A is delivering lagging reactive power. Therefore, the excitation of the alternator of part A should be used in practical situations. So in this way we have discussed example number 5.14 given on page number 598 of the book Electrical Machinery written by Dr. P.S. Bimbhra.